So I will just briefly talk about the seismic slope performance assessment, but the basics. I will just try to cover the basics. I am already aware that some of the participants here live at this event are very knowledgeable in the field, and I cannot do anything more than just introducing the basics of and go to hotspot points of what you should watch for while making a seismic slope performance assessment for soils. Slide 2 will be demonstrated for some of the concepts that we will use. First, we will just make a brief description about the decoupled and coupled analysis assumptions. They are mostly used in modern simplified approaches in predicting the seismic performance of slopes. Stress deformation analysis is nothing but a more rigorous analysis type. The basic form is just finite elements where you perform time domain analysis to capture the real behavior. If you don't have the tools, or in case you don't want to spend too much time on complex modeling, or else you want to calibrate your detailed numerical models with simplified approaches, then they can be used in conjunction. We will just say hello to equivalent acceleration concept, which is one of the main concepts behind developing seismic performance assessment of slopes and simplified approaches, and we will discuss about permanent displacement analysis. We will cover the basics of pseudostatic seismic slope stability. Of course, you know how it's done, but maybe a brief discussion on how the K factor should be selected based on your ground motion demands, as well as other parameters which are dependent on the slope itself. McDee introduced back in 1978. This is a method I love. With all the limitations noted, we will just say hello to how it's done, and this has been a path opener to more rigorous methods which built on McDee assumptions. And Newmark seismic analysis with a variety of options, they are already included in slide 2. We will see how, and we will just make a remark on what you should watch for while making a Newmark analysis. So from Professor Bray, beautiful paper. Here's a very brief coverage of what a decoupled and a coupled analysis is. In a decoupled analysis within an earth fill, you have a potential sliding plane. You capture the real behavior by using a dynamic response component and a sliding response component. You calculate the equivalent acceleration, horizontal equivalent acceleration time history, assuming that there's no sliding along base, and you superpose that system into capture the sliding response of a rigid block. Whereas in a coupled analysis, you are dynamically modeling the earth fill system as a flexible system and the base, and in a circumstance, in a condition where you assume for the sliding response between the base and the mass. Slide 2 can all handle these, and we will see what should be preferred and what is the difference between them in terms of a conservative or an unconservative output that is yielded. Stress deformation analysis, just a short reminder, the simplest form can be using a 2D finite elements or more complex tools and numerical models to capture the real-time behavior. Actually, it is idealized too. Time domain behavior of the slope. In case you don't have those tools, you are you have a good kickoff point using the equivalent acceleration concept. What it is the ground motion incoming to the sliding mass is incoherent within the as a function of time, and it's not uniformly acting to the dynamic response of the sliding mass. So you are just trying to make a simple idealization in order to express it in a more simpler way. What we call here is the equivalent acceleration. It is simply the ratio of the shear stresses along and a certain depth along the sliding mass, normalized with respect to the effective stresses. And so you use it to derive the K max value, which is very questionable and has a high degree of uncertainty, as we will see in the MACD and SEAT simplified method. Little bit of theoretical background. I should confess that I would love to provide you more information from the literature, but this is not the essence of this session. Maybe another session dedicated to this concept would be useful, and with the incorporation of a finite element solution. Okay, in the simplest form, what you can do to assess the seismic performance of a slope. Let's say you have a 10-meter height homogeneous fill. It may not be homogeneous at all circumstances, and you define a material strength. What is important here is that if you're after the seismic performance, you should be after the dynamic peak strength parameters to capture this performance in terms of assessing and calculating the factor of safeties in the dynamic sense, or the yield accelerations, which will cause the factor of safety fall below 1.0. In assessing your limit equilibrium models, it will be beneficial for you to use a model which incorporates the force equilibrium in 2 dimensions as well as the moment equilibrium. So you should also watch for the other parameters which are variables in the system, such as the unit weight, more importantly, pore pressures, and other crucial factors. The question is, should you use the static peak strength instead of the dynamic peak strength? It depends on the level of deformation you are expecting. Up to a certain point, a low threshold, you may stick with the peak shear strength parameters as you have determined for under static case. But K or Ky, the yielding coefficient in terms of a force solution, is dependent on deformation. So the more you are likely to build up some permanent displacements within your system, not yielding yet, but a considerable amount of shear strains to be accumulated, then you may have a drop in strength after a certain point. So in its simplest term, what you may stick with is just apply a little bit of 10 or 20%. That is what is most commonly applied of strength reduction to examine your slope for limit equilibrium analysis. A little bit of drop in strength will do no harm. Under very large deformations, things are different. Again, in order to use all these analyses, the basics is if your material is likely to lose significant strength under cyclic loads, dynamic loading, either harmonic or earthquake, then use these methods with caution, or do not use these methods at all, as they will be defined under flow slide definition, and these simplified methods won't work at all. Back to pseudostatic analysis, our simplest form. Here you have a driving force in both directions due to dynamic effect, and they are proportioned by the mass of the sliding surface or the volume. What you can do in slide 2 is, we will not cover those in detail and will not be able to show you a demo, but afterwards this session, if you're interested, we may gladly set up a custom demo for you. We're building another scenario within slide 2 and name it Pseudostatic. You can work with scenarios, multiple scenarios within a single defined file. So you can manage all of your different scenarios, either static, dynamic, or models which incorporate modifications in groundwater levels, pore pressure distributions within a single file. You're able to define them and manage it within a single working file. And that would also comfort you in your everyday tasks, as well as it will cut down on the total runtime, by the way. In the simplest form, you can define a seismic load in slide. In our case, it's 0.15 in the positive direction of failure, and see how the factor of safety is changing. A crucial issue here is once you apply the seismic loads, then you're not necessarily getting the same critical failure surface as you do for the static case. Please keep an eye on it. How to choose K, we will go back to it, but I should say that mostly they are dependent on the level of risk that you will undertake for that specific project. Either you will be, speaking of the dams, for example, either you will be dealing with an operating basis earthquake, which will bring you up to a 145 years return period ground motions, then you will evaluate those results, and you will face another questions about how whether to reduce them within the soil mass and how to reduce them. We have some more recent tools in the literature that lead you beautifully to selecting the K factor as a function of not just the input seismic demand, but also on the order of allowable displacements you are expecting or you are to tolerate within your confines of the project. Period of the structure, which is the period of the sliding mass itself, earthquake magnitude, and you can also incorporate a level of uncertainty within these simplified models to come up with a really good risk-based approach, even though when you're still using the K factor. A second method, a McDissy and Seed 1978. We're introducing this because this is not the latest. This is one of the first methods. However, the latter methods, the future generations of work mainly relied on these and in improving the assumptions, simple assumptions that McDissy and Seed have published. By the way, if you are after just calibrating or getting a good cross-check for your detailed numerical models incorporating time domain analysis, McDissy and Seed or other empirical methods are still an invaluable tool that will enable you to check your performance of your numerical analysis within a matter of minutes or seconds. There are simple assumptions for the McDissy and Seed method. It is not directly included in slide 2. However, it requires a parameter, ky, the critical acceleration, which you will reach the critical state, a factor of safety of unity, will be derived from a slide analysis. Then you can go on with McDissy and Seed's charts to complete your task. One other option, ky in slide 2 may be determined by a sensitivity analysis or by using advanced seismic settings. I personally prefer to use advanced seismic settings within the dynamic seismic options within slide 2. I don't think I have much time in repeating the basic assumptions of McDissy and Seed. However, please make sure that it is kept within your notes, and it is intended to be developed for a range of small seismic displacement interval. It's not intended to be used for large displacements. And furthermore, there is a small database compared to newer generations of work that charts were derived for MACD-CNC. So magnitude scaling and other issues, please keep an eye on them. However, these will just provide you a means of how you are doing. Well, the first step in the evaluation is defining your material strength loss potential. We have talked about this a moment ago while dealing with the selection of the K factors, so I'm not going to repeat it again. In the second step, based on these criteria, calculate KY. All within a limit equilibrium analysis, it will yield you the horizontal acceleration value, which will trigger the instability conditions. Then you should be able to have a feeling of how the accelerations will vary within the sliding mass itself, because in reality there will be the response of the sliding mass itself. On the upper right portion, you can see a study made by Bray and Rocscience, Professors Bray and Rocscience, back in 1998. This is calibrated for a waste fill. Please be cautious. It's not suitable for every type of fill. And you can imagine and you can directly observe the great deal of uncertainty for selecting the equivalent acceleration, the Kmax, not the Ky, and the relation of it with the crest accelerations. So we have three parameters. It's the Ky, it's the yielding accelerations, which will cause instability. Then you have some parameters about the response of the sliding mass itself. It's the Kmax. Kmax is defined as the maximum of the horizontal equivalent acceleration, the concept we have introduced a moment ago. And it is surprisingly, or not surprisingly, dependent on the crest accelerations. So where you get to crest accelerations, that's the problem. If you are able to measure it, then you have a real specific case. You can go back and measure and calculate your Kmax for that case. If you don't have it, then your tool would be going back to a more rigorous finite element analysis to capture the crest acceleration. So that may be a little bit of conflict for discussing, so what's the use of a simplified approach if I have to go back to a full numerical time domain analysis to use a simplified method? There are actually some earlier generation charts to have just a feeling of what the relation between a crest acceleration and Kmax can be, or you have some later generation works which will enable you to quantify the uncertainty and estimate Kmax within a more comfortable band of uncertainty. So we will just follow what MACD-CNC has done within an example a moment ago. But if you don't have a limit equilibrium tool, which is out of question nowadays, here are some very simplified methods for estimating KY, calculating KY for a shallow slip or a more deeper slip. If you don't have a numerical tool, you may just use them. Else, preferably, you can directly calculate KY for any geometry and for any slip surface using slide 2. Here we add another scenario to our system named as critical acceleration. Then you compute your seismic analysis using the factor of safety or target factor of safety, which is 1 for this case, and it calculates the KY for all potential failure surfaces and tells us what is the critical failure surfaces and what is corresponding KY is. This is something you may not fully capture using a sensitivity analysis within slide 2. So stick with this if you're after KY. Here it is, 0.146 for our case, a very simple model. Then what we do is we have a candidate earthquake magnitude, we have a PGA value, and we have defined our KY value from a limit equilibrium analysis. So you go back to your geometry, which gives you the most critical slip surface and have a ratio of the depth of that critical surface with respect to the height of this original slope. In every analysis, you may not come up with such a result. But here, for simplification, as we have again used an homogeneous slope, this is what we have received. The y/h ratio is almost equal to 1. So from Mac-Seitz graph, you define a ratio of Kmax divided by the crest acceleration as 0.34. Then, assuming that it is a landfill, you go to Bray and Rocscience chart and try to estimate the crest acceleration as a function of PGA to be encountered at the project site, which is basically the ground motion intensity that you derive from a site-specific hazard study or a code-based hazard map. Once you plug in those variables, you get the value of Kmax being 0.19. And lastly, you go back to Mac-Seitz last chart, which incorporates the ratio of KY to Kmax. And as a function of earthquake magnitudes, you are able to approximately derive the range of permanent displacements for your analysis. Please also keep an eye on that the magnitude range intervals are too broad, and they are just aimed to give you a feeling. More detailed method, Newmark sliding block theory. In Newmark sliding block theory, you have 3 options in slide. Whether to A, to assume everything is rigid, B, you are able to make a decoupled analysis, and C, you are able to conduct a fully coupled analysis. So in case you're preferring a fully coupled analysis, the software will ask you some basic questions about the approximate stiffness, namely the shear wave velocity of the sliding mass and the underlying slope surface. So the basics of Newmark, it's not something new, I know that, but these are just reminders. And you can complete your analysis for estimating your seismic deformation in a matter of seconds or minutes within slide 2. As defining another scenario and using your readily available 2D model. The basics is, the essence is, once the threshold acceleration is exceeded in terms of a strong ground motion input into the system, the block moves until its velocity is again 0. So a block within a strong ground motion can trigger movement more than once, or no movement at all. It is fully dependent on the characteristics of the ground motion that you are inputting, as well as the KY value that again also you can derive from your previous steps of the analysis. This is just to ensure that the movement does not stop once the threshold acceleration exceedance has stopped, because single integration will lead you to velocity, which means that there's a phase of slowing down, and there's also a small displacement buildup. And once the velocity is 0, the system is undergoing 0 displacement until it is exceeded again. I am just passing these very quickly all detailed descriptions and repetitions of what I have trying to remark. Very basic equations behind the Newmark sliding block theory. Again, you can define a new scenario for conducting the Newmark analysis. Now you have to say you are activating the Newmark displacements and go with the options. You can define whether the displacement would be single direction only downwards, or you also have the option to incorporate upslope movements due to very strong inverse accelerations, which will cause the mass to go upwards, pushed upwards. We are aware that a great deal of upward effect should be acting on the body to cause it moving in the upward direction. And if you are not trying to be under conservative, you can just go with the downslope direction only. The options are easily chosen. Literature has the full documentation behind the implementation of this method. Just a very simple result. When you solve using the Newmark sliding block theory in either of the methods, here we have solved with the rigid, with the coupled and the decoupled analysis, and have documented using the Spencer's method to document the permanent displacements anticipated for this site. So what would be, if I use all of the options, what would be my best choice? Shall I stick with rigid, with coupled or decoupled? And how can I differentiate between and the results and interpret them accordingly? Again, literature has provided us very good documentation on how they perform. Let me put it that way before concluding, because we are approaching the end. Okay, I have in my notes, as we said, actually the behavior is dependent on the strong ground motion characteristics, perhaps most successfully defined by the mean period of ground motion, input ground motion, and its relation with the period, initial natural vibration period of the slope. So if you have something close to 1, the Ts over Tm, then the rigid assumption is somewhat unconservative compared to a coupled analysis. So to put it in a different way, if the period of vibration of the sliding mass is very large compared to the natural period of the strong ground motion itself, then rigid is somewhat conservative compared to a coupled analysis. So differentiate between a coupled and versus a decoupled analysis. If you are after small deformations, say less than 1 centimeters, then choosing either of these, either decoupled or coupled, would give you a similar solution. If you're after, or if you're expecting large deformations, say in the order of 1 meter or more, then your decoupled analysis would be more conservative by multiple orders. If you are between, let's say, 1 centimeter to 1 meter, then choosing decoupled can be unconservative for some cases. And the simulations published in the literature have shown that that level of unconservatism can be remarkable up to some extent. So before summing up, maybe back to our preference of selecting your K value for pseudostatic analysis, you may enhance your vision to include not just only the seismic demand for your scenario, but its relation between the period of the sliding mass and the earthquake magnitudes and the allowable displacements using the readily available published literature for estimating the simplified seismic slope displacements. Another last remark with apologies and thanks for your enthusiasm in following us. Is one strong ground motion set enough? Surely no. This is a very small, very basic exercise, which we have selected two horizontal pairs of ground motions from 6 different ground motion sets. I can imagine that you will have comments about whether on the selection preference, because they are more constrained to 6 different ground motions from 2 different earthquakes. We may just vary them, no worry. Okay, we have put up a target spectrum, magnitude 7 earthquake, about 15 kilometers source to site, distance, strike slip mechanism, 4 ground motion prediction models equally weighted, and came up with a target spectrum. And we have searched our records, strong ground motion records for shallow crustal zone earthquakes from the PEER database. On the left-hand side, you can see where the blue is the target spectrum, the red solid line is the geometric mean of every component used to match the target spectrum without any individual scaling. So in the average, they match this target spectrum, but they are not necessarily scaled and have a higher level of deviation from the median compared to the case that they were intentionally scaled individually to have a better match to decrease the variability. So the mean around the target spectrum in these 2 cases are the same, but the level of variability is changing. Here's what we have. If we just put them under the same Newmark sliding analysis, you can see that based on the KY is the same, but the Kmax will not be the same here in this case. So depending on whether it's scaled or the level of scale factor to be used to match the target spectrum, the displacements encountered and obtained for the individual strong ground motion records can vary within a notable amount of range. So this is just a point of discussion. I am not intending to conclude or put any more pressure on you while listening me, but I am also aware that literature has also some solutions and recommendations on how to properly select your ground motion sets to be included in a simplified seismic slope analysis. And I'm just bringing the question and our very small remark to you. Ladies and gentlemen, thank you for your patience. It's today Octavian Bujor, Ferenc Deák from our friends from Romania and Hungary, and me, myself, on behalf of the GeoDestek group, would like to thank you before summing up. I can see that you have a couple of questions in your typed in the question box. We will try to answer them as much as we can after the session has ended. For your trial setup and sales inquiries, you may contact us. And please note that Rocscience will be organizing its first international conference on April 20 and 21st. The details are available on rocscience.com, as well as the registration information. And please should be sure to secure your spot in the event, which there will be panelists, presentation of papers, and a good amount of geotechnical fun 2 months ahead of us. Thank you very much.